Well, today we're talking about Chapter 2, Section 2, the derivative of the exponential function, which would be base e. So let's put this on the current page, 2.2. Right, so since this is um, this course is mainly for business and education majors, calculus for business and education majors, we're not going to necessarily talk about the rigorous proof of e to the x. Instead, it's obviously, well, it's not obviously. Some of it is provided here on the text. If this were a STEM calculus 1 sequence, then we would go over it. But since it's not, we will not. But we will actually snip this whole thing here. Right. So today is going to be a pretty simple day, pretty simple and I think pretty short, mainly because the major concept for this section is super easy. The derivative of a function f given by f of x equal to e to the x power, right? So the derivative of e to the x is going to be e to the x. That is the title topic of this section. Now, obviously, there's going to be other things involved, but that's really it. We're just focused on e to the x. And let me mute everybody real quick. So anyways, yeah, we're just simply focused on e to the x. And the derivative of e to the x is e to the x. So let's do some brain busting examples here. Okay, and again, we're gonna be talking, we're not talking, we're gonna have examples where we have to do, product rule, quotient rule, chain rules, things like that. But that's concepts that we've covered before, right? Instead, the main focus is just basically, gonna be kind of focused around e to the x. And honestly, actually, I forgot to, I got a little ahead of myself. Did I? No, I didn't. Okay, because I think we talk about that on the next page. Yeah. Okay. So we're going to talk about example 1, and that is here. So we need to find dy dx, right? And again, that notation is find the derivative of y, and that dy right here corresponds to this y here, right? Because that's just basically the name of the function, y, with respect to x, and of course that's the variable. So again, just to briefly cover that notation there, that's what that means. All right, so A, we need to find the derivative of 3e to the x. Okay, well, we know we can essentially write that as 3 and then find the derivative of e to the x. Right? And again, this notation just basically means find the derivative of, what follows. Right? Well, as mentioned, the derivative of e to the x is simply e to the x, so this is just 3e to the x. Super easy stuff, right? Right? But I promise you it gets a tad harder, but not much. So b, we have y is equal to x squared e to the x. Okay, so this, notice, we're going to be doing the product rule, right? First times the derivative of the second plus the second times the derivative of the first. So let's begin. So first, which is x squared, times the derivative of the second, which is e to the x, plus the second, which is e to the x, times the derivative of the first, which is 2x. So this becomes, shoot, I'm probably going to put c on the next page. Yeah, we'll just roll with this and put c on the next page. I don't like it looking horrible for the notes. But anyways, so we have x squared times e to the x plus e to the x times 2x. We see that we can factor out an e to the x there. Actually looks like we can factor out x e to the x. So we can factor out x e to the x. And what remains is an x e to the x. No, I factored the e to the x out, sorry. Plus 2. Alrighty, and that's b. We're just going to, like I said, put c on the next page because we want this to look somewhat presentable. Right, so it appears we're going to be doing the quotient rule here because we have a quotient. So C, we have y is equal to e to the x over x cubed, right? Well, again, we have to do low d high minus high d low, right? So low, which is x cubed, times the derivative of high, right? Low d high, which is e to the x, minus high d low, which is e to the x, times the derivative of the low, which is the d low part, which is 3x squared. And that's all over low squared, which is going to be x cubed squared, which is x to the sixth. All right. And let's clean this up a little bit. It looks like we can factor out an x squared and an ex. So we can factor out an x squared e to the x out of the numerator. And so that leaves us with an x minus 3x, 3 minus 3. And that's all over x to the sixth. Right? And then the x squared cancels with two of these, so that goes down to a 4. And of course, I'm going to go ahead and erase that so I don't have, well, now I'll move it to the right. Let's not erase it. Let's just move it to the right. I mean, left. The other right, right? The other right. So we're going to do this. So we're going to end up with simply an e to the x times x minus 3 all over x to the fourth. Okay, so example 1, A, B, and C, not abundantly difficult. We just had to remember our product rule and our quotient rule pretty much. Right. Next up, we're going to figure out what if the x on e to the x is an actual function, right? If it's not just a simple x. Well, that's where this comes in. So this reads, the chain rule is needed when differentiating functions of the form g of x is equal to e raised to the f of x. Okay, so now this notation, don't let this notation scare you. All it's simply saying is that e is being raised to some function, right? It can be any function. For example, here's some examples down here. We see that e is being raised to the 8x. We see that e is being raised to the negative x squared plus 4x minus 7. And then e is being raised to a radical, which is, silly, but that's the way it is, right? So that's all that means. That's all that notation means is you're simply raising it to some function, right? So if we take the derivative of that g of x, well, actually I didn't even finish reading it, did I? Note that if we let h of x be e to the x, right? So h of x is going to be e to the x. Then we have g of x is going to be the composite function, and again, look, for the record, all this here is just simple notation. It's just kind of showing how we derive something. Again, if I were you, again, not going into a STEM field and not needing this rigorous proof, I wouldn't even bother trying to memorize all this. I mean, is it cool to know? Yes, it is. It's also nice to know where it derives from. But again, I also know that today being almost the middle of the semester, that your brain power is slowly grinding to a halt between this class and other classes. And I'm just giving you a pro tip. This is all just mathematical notation. But we will continue. I'm just saying that, when I start saying, composite function this, e to the x, h to the x, don't get too wrapped up in that because this theorem really wraps it up nicely. Anyways, if we end up having the composite function h of f of x, which again we know we can write it like this, right? Thus, we take the derivative of our g to the x, all right, which is the same thing as taking the derivative of that composite function, and we end up with, down here, e raised to our function times f prime of x. So what does that mean? What this means is we take the e to some function of x, and then multiply it by whatever that exponent is. And that's all it's saying. And of course, let's see. None of these really, well, this part of the theorem, I guess this part of the theorem is the same as this part. But if I want to take the derivative of some e, and it's not raised to the x anymore, it's going to be raised to something else. It's going to be raised to some function, okay? We know the derivative of e to the x. That's e to the x. But if we have e to something, e to some function, then it just becomes e to that function times the derivative of the exponent. Right? So let's put that into motion so you can actually see some examples and to really drive the point home. And actually, let's go ahead and snip the theorem along with it just so we can follow along. And I can really show you. Alrighty, so A is y is equal to e to the 8x. Okay, so my function, all right, is I'm sorry. Well, my exponent is some function. So in this particular case, let's actually do this very slowly. Let's go. Let's say f of x is going to be equal to 8x. Okay, so just following along with this first little bit of notation here is all I'm focused on. So if I have e raised to some f of x, we see that e is indeed raised to f of x, right? Because I said f of x is 8x, right? So I'm just going to go ahead and erase that f of x and put the 8x there because that's what I said f of x is. Okay. Well, if I followed along with this theorem, then the derivative of e to the 8x is simply, I'm just simply going to rewrite, I'm just going to simply rewrite my exponential form there. So it's going to be, let's actually put d dx here, right? That just means I'm taking the derivative of it. Is going to be equal to, well, I'm just going to rewrite my exponential form like that. Okay, and then I'm going to multiply it. That's horrible. Then I'm going to multiply it by the, right here it says f prime of x. So it looks like I'm taking the derivative of the exponent. My exponent here is 8x, so the derivative of 8x is 8. Right? So all this boils down to is 8, or my solution is 8e to the 8x. And let's see, let me see if I can move this around just a second. Put up just a tad, and then I'll erase that and make it prettier. Okay. Anyways, that's it. That's pretty darn easy, right? So let's go ahead and do that with B. And C is probably going to get its own page, so we'll just go down here. So the derivative of B, which is, B is e raised to the negative x squared plus 4x minus 7. I'm just going to rewrite that. That's all I'm going to do. I'm just going to rewrite it. Negative x squared plus 4x minus 7. And then I'm going to multiply it by the derivative of this. And of course, we know the derivative of, well, we don't know off the top of our head, I guess, but we know how to do it, right? Well, I can just take the derivative of this in chunks, right? Well, what is the derivative of negative x squared? Well, that's going to be a negative 2x, okay? And then, well, I guess I don't have to do that. Negative 2x, and then plus 4, right? And the derivative of 7, well, that's just 7. And so I can, I mean, honestly, it's not too bad, but I multiply this, and looking here, it looks like I can go ahead and factor a 2 out. So it's going to be 2. I factor a 2 out. I have a negative x plus 2 times e to the negative x plus 4x minus 7. Okay, and all I did here was take this line and make it nice and pretty. Putting the 2 times negative x plus 2, this part, in front of the e. So that's it. Again, super easy, I think. We just take we take the exponential function, and then we take the derivative of the exponent, right? Of the what we're being raised to. And let's do that again. We'll do c this time. And we'll just keep the theorem there. So c, we have, again, we're just going to rewrite e to the well, I guess we'll go and write the square root x squared minus 3. And of course, this looks like it's going to be a chain rule, right? Because the derivative of this of this particular function is, well, I could rewrite it, right? I can rewrite this as x squared minus 3 raised to the 1/2, right? And then this, if I take the derivative of it, and shoot, I'm just running, I'm all sorts of running out of room here. All right, I take, it's 1/2 times x squared minus 3. Yep, definitely run out of room here. And then I subtract 1, so it'd be negative 1/2. And then I take the derivative of the inside there. It's just a chain rule. And let's see if I can. We just won't put that there. We'll just take the derivative and put it out to the right here. All right, make it nice and neat. So again, like I said, I have 1/2 times x squared minus 3 raised to the negative 1/2 power. Let's fix that. Negative 1/2 power. And then we're going to take multiply that by the derivative of the inside there, which is simply going to be 2x, right? Because the derivative of negative 3, well, that's just 0. And then if we clean this up, it looks like the 2x times 1/2 is just going to be x, and we can put that out front as well. So we're going to say it's going to be x, and then e raised to the x squared minus 3. All right, and it's going to be all over the square root of x squared minus 3, right? And the reason why is because looking right here, okay, and again, this 1/2 times this 2x, that's what got me this x. And then I multiplied that x times the e raised to the square root of x squared minus 3. But circling, or what I circled there in the red, goes into the denominator because we have a negative exponent. And if I want to make it a positive exponent, it goes into the denominator. And then, of course, if we have something raised to the 1/2 power, then that is a square root. So hopefully that really drives that point home. Okay, we're not done yet, but it is a pretty short section. Oh, I guess I just want to do this. All right, as you can tell, this is a pretty short problem, but we'll work it out. All right, so what this is saying, and again, notation-wise, you've seen this notation before. This means find the second derivative of my function here. So the way I go about doing this is, well, I first got to find the first function, right? So I'm going to say, I'm just going to write the first function, which is d dx. We're going to take the derivative of e raised to the negative 5x squared. Okay. Well, if I want to take the derivative of that, well, all I have to do first is, again, rewrite my exponential function. And then I'm going to take the derivative of my exponent there. Right? So multiplied by that, so it becomes a negative 10x. So my derivative is going to end up being a negative 10x e to the negative 5x squared. Okay. Now finding the second derivative, we're going to have to do the product rule, right? Because we have the first times the derivative of the second plus the second times the derivative of the first. So proceeding here, we're going to do the first, which is negative 10x, times the derivative of the second. So the derivative of the second is going to be, let's do this. And let's actually focus in on this real quick. I'm gonna do the computation down here and then erase it. Okay. So what is the derivative of e to the negative 5x squared? Well, it is e to the negative 5x squared times the derivative of the exponent there, which is going to be a negative 10x. So that is the derivative of the second term, and of course if we clean it up, I don't necessarily have to write it out here, because I'm just going to erase it. But we put that multiply right here, so it's going to be negative 10 x e to the negative 5 x squared. So that's first times the derivative of the second, and then plus the second, which is e raised to the negative 5x squared, times the derivative of the first, which is a negative 10. All right, and shoot. All right, so if we clean all this up, it looks like we can factor out a 10 10e to the negative 5x squared, 10e to negative, and then what remains is a 10x squared minus 1. Okay. So all we did was take this, or find the second derivative of this function, and again by just taking the first derivative and then taking the derivative of that derivative. All right, it's an exercise we've done before, but this time we have exponential functions. All right, so now applications. So this is the fun part. Right. I do like how the text, how this particular textbook, it asks, um, find what we need to find, but then interpret the meaning of each of these values. I really like that about this textbook, because for the most part, a lot of the times you just do computation and then you're like, okay, so what is this for? Well, we're gonna talk about it. So example 4 reads, Franco's, one moment. Alrighty, so Franco's Fishing Emporium invested $50,000 in an account that earns 1.25% annual interest compounded continuously. The value of the account after 2 years is given by our function here. Okay, so we need to find a of 5 and a prime of 5 and interpret the meaning of each of these values. Okay, so this is just going to have to be something I unfortunately put into my calculator. It's one of those things where it's just kind of awkward, where I put something into my calculator and you just kind of sit there and wait. Okay, but if I want to find a of 5, right, so a of 5, all I'm going to do, I'm just plugging in the value of 5 into my variable t there. Okay, so I'm just going to put in my calculator 50,000 times e raised to 0.0125 times 5. Okay, so I'm just evaluating at 5, and give me a second. 50,000 times e raised to the 0.0125. And for the record, I think it would be helpful for you as a student, whenever I put this into my calculator. This is what it looks like. I did 50,000. All right, and again, you probably know your way around a calculator, but you, as a student, again, I say this because I was that student. You sometimes you put something into the calculator wrong, and so what I do is I just go absolutely positively overboard with parentheses, and so I put this into my calculator. It looks like this. Times 5. All right, and this tells me that we're raising e to that product. And that, whereas if you were to just, if you didn't put your parentheses there, then it would just simply look like the calculator might interpret it as e raised to the to this power, and then all that times 5. So parentheses do matter whenever you put stuff into the calculator. I'm sure many of you have at one point or another put something in wrong into your calculator, and you're like, okay, my calculator is stupid. Yeah, but unfortunately, it most of the time, 99.99% of the time, is user error. But anyways, I ended up getting $53,224 $224.72. Okay. So after 5 years, so interpreting the meaning of a to the fifth power is that after 5 years, my account that I deposited $50,000 into grew $3,224.72, which, by the way, is pretty bad. I mean, 1.25%. I mean, the S&P 500 I think averages something about 11% a year. Now, at the same time, that's the average. I mean, you could hit a bumpy road and you invest and um, in 3 years you actually might lose money, but over the course of 20 30 years I think you'll be better off than a 1.25% annual interest. But it's for you to decide. It's your own what's called risk tolerance. Anyways, next up we need to find a prime of 5. So what we need to do now is we need to find the derivative of a of t, find the derivative, and then uh, substitute 5 in for t. Okay, so finding the derivative of this function is pretty easy, I think. This is one of the easier ones we've done today, minus example 1, I guess. So we would say 50,000, all right, and then we're taking the derivative of that of the function with respect to t of e raised to 0.0125t. Well, that just becomes 50,000, and then the derivative of that is e to the 0.125t. And then what's the derivative of 0.125t? Well, that's just going to be 0.125. And then we're going to, if we combine like terms essentially, right? We have 50,000 times 0.125, so 12.5% of 50,000 is going to be 10% is 5,000, so 625. So we'll have 625 e raised to 0.125t. And this is a prime of t. Okay. Well, if I wanted to find a prime of 5, again, all I'll have to do is simply plug in a 5 right here for t. So let's do that. I probably shouldn't have cleared everything. Oh well. Times e raised to the 0.125 times 5. 625 times 8. Oh, I know what it is. Once again, I put in the wrong number there. I still did 12.5%, or yeah, of 50,000, but it is 0.0125 times 0.125. Okay, so let's try that again. So that would be 665. That makes more sense. So a prime of 5 is equal to 665.31. Okay, so what does this mean? All right, so this means that at the instantaneous rate of change, right, which is what the derivative is, the value of this fisherman's account is growing at $665.31 per year. So again, that's what that means. So a of 5 is what we have after 5 years, and a prime of 5 is the instantaneous rate of change, how fast we're growing in those 5 years. Okay, and for this one, we're going to go ahead and we're not gonna snip all of the solutions, but we are going to snip some of them, mainly the graph and A. Because again, this is just calculator work, and it's just, I think, as a listener, it's easier to just see this as opposed to hearing me punch into a calculator. Okay, so this is B. Alrighty, so looking here, we have the worker output. So it is reasonable for a manufacturer to expect the daily output of a new worker to be low at first, increase over time, and then level off, which makes sense, right? Because if you're a new worker, you don't really necessarily know what you're doing, but the more you do it, the better you get, and then you eventually get to a point where you level off. You're only making a certain amount of light bulbs a day. Like you've gotten pretty good at what you're doing. So that makes sense. So a manufacturer of LED flashlights determines that after T work days, the number of flashlights produced per day by the average worker can be modeled by this equation. Right? So find N for T is equal to 1, 5, 10, 20, and 30. So all we're doing for A is plugging in these values for T. And we see that here. Okay, so when T is equal to 1, my NFT, or the amount of, I guess this would be the amount of flashlights I can make, LED flashlights I can make, are about 19, right? It was T days, yeah, T work days. So in one day, I can expect to make 19 flashlights. In 5 days, I can expect to make 44. 10 days, I expect to make 61, and so forth. Okay, and by the 30th day, actually, I can expect to make about 79. Right? And then B says graph N of T. So you just take this, put it into Desmos or your graphing calculator, and then your graph would end up looking like this. Okay. So C reads find N prime of T and interpret this result as a rate of change. All right. So to find N prime of T, all I have to do is take the derivative of the function N. Right? I mean N prime. That's all it means is take the derivative of it. Okay, so this becomes, and if I want to, let's do the notation. N prime of T is going to be equal to, well, the 80 doesn't really go anywhere, right? Uh, well, it does go somewhere because the derivative of 80 is 0. Uh, so we're going to be stuck with, not stuck with, but we're going to basically just going to be differentiating this. Okay, so it looks like what we're going to do is we're going to take the negative 70 and then times e raised to the negative 0.13, 0.13. Let's make sure we do this right this time. Right? And then what is the derivative of my exponent there? Well, that's just going to be 0.13. So it's times 0.13, negative 0.3. Let's fix that. Times, I can't make a nice good multiplication on here, but that's just the way it is. So negative 0.13. All right. And then, well, I don't really care to do that in my head, but so I do negative 70 times a negative 0.13, so it's 9.1. So this ends up being 9.1 e to the negative 0.13 t power. And that is n of, or I'm sorry, n prime of t. Right. And then d, I guess that we don't want to figure out, any sort of rate of change there. But D, what number of flashlights seem to be the number at which worker output levels off? Now, we can do this. We could do this looking at the function or graphically, and I think at this point we are going to be looking at this graphically. because we haven't really went over how to look at it algebraically, but it's pretty easy. It's just 80, right? That's the oh shoot, what's the word for it? Carrying capacity, I think, right? 80 minus, our function there. But if we just look at this graph, we look like we do indeed level off at 80, right? So looking at the graph, it looks like, the longer you're there, you're tending towards making 80 LED flashlights per day, right? And I believe that is the last bit. Yeah, and then we'll hit the section summary, which this is probably the smallest section summary that we've had. And that concludes today's lecture.